Welcome, dear civil engineering people. So today we will be seeing about the deflection of curved bars. Now, these bars are also known as curved davit. The meaning lies here with the davit being used for lifting the weights as well as the boards in the ship. So this is the main shape of the bar, and it is called popularly as davit, curved davit, and also called as curved bar in colloquial language. So proceeding further, we will derive the expression for finding the vertical and horizontal deflections. So you can see that here we are applying only the vertical load that is present here, and for this vertical load we will be trying to find out the horizontal deflection as well as the vertical deflection. So you can see the picture is a replica of structures used, and this is generally called as a structure resembling the lamp post. This curved type of structure could be used for building sheds for cars or any other steel structure that could be used as a davit in lifting the loads. So commonly used in the shipping yard, as well as this resembles the shape of the lamp post. And also you can see that these type of structures could be used for the industrial steel sheds. So we can see that these are the expressions. Del V is equal to PR squared by 4EA into pi r plus 4H, and del H equal to PR by 2EA into R plus H the whole square. Now you can relate that this WV is nothing but the P. So that is the load, and you can here see the formula for del V and del H. Now we will use strain energy method. Here you can see that the load is applied here, and because of this load from this point to point A to point B, you will have an expression. This is the expression for point A to B. So for point A to B, you have the expression here. Then for point B to C, the moment expression varies, and the limit also varies. So here there are the limits that for the point from A to B, you can see that the limits are between 0 to pi by 2, and for B to C the limits are between 0 to H. So you can see that this point B to C, the total height is said to be H, and you can see that the variable is Y. Here at this location B, Y equal to 0, and at the point C, Y is equal to H. So you can see that you can vary the 0 to H, and the general expression here is WV into R. So this WV at this point B will create a moment of WV times R. So WV times R, that's what we get here. Now we will use strain energy method. So the expression for strain energy stored is U is equal to M square ds by 2EA, and ds, as you see, it is equal to R into d theta. If you have a curve like this, and this is said to be the arc length ds, and the theta is here, and the distance from this point to this point is the radial distance R. So basically this ds is obtained from this R into so this is theta, or it could be d theta. So R multiplied by d theta is the ds. So that is represented here. Now as I told you, the moment expressions are from point 0 to pi by 2, we have WV into R sin theta, and the moment expression for 0 to H will be WV times R, and the formula for strain energy is M square ds by 2EI, and here it is split into two expressions. And once you apply the limits and do the integration, you end up with this expression. Then we can use the Castigliano's second theorem. So it states that del I equal to dou u by dou wi. Now you can see that this del I is the Castigliano's theorem. It states that deflection at any point I is equal to the partial differentiation of the strain energy with respect to the particular load applied at that location. So here the strain energy is uptime, and you take the partial differentiation. So del V is equal to dou u by dou wv, and finally you end up with this expression del V equal to wv r square by 4EI into pi r plus 4h. So Castigliano's second theorem plays a role here, which uses the strain energy to calculate the vertical deflection. Now, how to find out the horizontal deflection? Now we know that we apply only the load Wv. We have not applied any horizontal load. So no horizontal load is applied. No horizontal load. Is applying. So definitely this is going to be a good example for dummy load method also. So these type of methodologies here, we play a tricky thing. We apply a load WH, which is horizontal load, and you can see that WH is nothing but dummy load. So dummy load in the sense, we will use this WH to find out the expressions of strain energy, and we will differentiate with respect to WH, and finally we will put WH is equal to 0. This trick we will play here, because we need the horizontal deflection only for WV, and we don't apply any horizontal load. If you really apply any horizontal load, then that case will be different. So here we apply only vertical load, which is WV, and WH is going to be the dummy load, and we will put 0 at the end after doing all the derivations. Now how to calculate this? First you find out the expression for strain energy using WV and WH, and substitute dummy horizontal load is equal to 0 and find out the horizontal deflection. Here the challenge is finding out the expression for moment at this point x, which is due to WV. So you can see that WV is at a distance. The value of the lever arm distance is r sine theta, and if you take the lever arm distance between point x and the horizontal load WH, you will find out that this lever arm distance is going to be r minus r cos theta. Then if you take r outside, r into 1 minus cos theta. So this is going to be the lever arm distance for the load WH. So with this, we enter into strain energy methodology. So the strain energy is equal to m square ds by 2ei. Now you have got the expression for 0 to pi by 2, having the expression WV WH into r d theta. So ds is r d theta divided by 1 by 2ei. Then you take the expression for integral between the limit 0 to h, where you have WV into r plus WH into r plus h, r plus y the whole square. So WH into, for example, if you take this point, this lever arm distance is nothing but WV times the lever arm distance is here, it is r sine theta. Now for WH, this would be the lever arm distance, which is nothing but this distance is r and this is y. So finally you have r plus y. So this is the lever arm distance for WH. Don't worry about WH, you finally end up putting WH equal to 0, because WH is the trick we play by applying the dummy load. And you can see that the del H expression is differentiating this expression, this equation, 2m into dou m by dou WH into r d theta by 2ei plus 0 to h 2m into dou m by dou WH into dy by 2ei. So here you have m square, and if you want to differentiate this, it will be 2m into dou m divided by dou WH. Note down that you are differentiating with respect to h. So using this expression, we are going to estimate the deflection, which is horizontal deflection. Now you can see that after differentiation we will apply WH equal to 0. So this expression is going to be 0 and this expression is going to be 0. Then you have del H equal to this WV r cube sin theta minus sin theta cos theta d theta by ei plus 0 to h WV r square plus ry into dy by ei. So sin theta into d theta is equal to 1, and sin theta integral 0 to pi by 2 sin theta d theta is equal to 1. And similarly you have here sin theta cos theta integral 0 to pi by 2 will be equal to 1 by 2. So substituting all the values, finally we end up with del H equal to WV r by 2 ei into r plus h the whole square. So thus we obtain these two expressions. Finally this WV could be substituted by the value of P. This load is nothing but P. Now here you will find out that there is no horizontal load, and WH was used in the play for finding out the horizontal deflection, and finally we put WH equal to 0, and so that only the effect of WV is used for having the vertical deflection and horizontal deflection. Thanks a lot for watching. If you have any doubts, queries, please mention in the comment section and subscribe the channel. Thank you.